Martinez, Linzy Franks, Noah Larsen, and we're going to be discussing the design and implementation of affordable site technology for the blind. We're going to be talking about our problem definition, prototype image, design constraints, engineering standards, show a functional block diagram, a schematic and hardware, our parts list, a projected budget, a Gantt chart, and our plan for an end product demonstration. For blind people, they have three means of navigation. First being a seeing eye dog. Seeing eye dogs are really expensive. You have to feed them, take them to the vet, make sure they're healthy, and there's usually a waiting list for those. Second, if you don't have a dog, then you can use a cane, and a cane doesn't give much information except for when it comes into contact with something. So there needs to be a way to know maybe if something's coming before you get to it. And with our project, we're going to use sonar technology, where we're going to send out a signal and it'll bounce off an object and send information back. This is a rough draft of how it's going to look. We're going to have two sonar sensors connected to an Arduino microcontroller. It'll have a braille system with a clock that tells the time of day, also a pedometer that'll tell how many steps have been taken, and a vibrating armband with a speaker to give audible commands and information. Some of the design constraints that we've been facing: economic, we want to keep it affordable so that everybody can use it. Environmental, we want to keep it portable, and we want to make it out of recycled materials so it's good for the environment. Social and political, we don't want to give a false sense of security to our users. It's not going to solve their problem, but it's just a tool and it has drawbacks. Ethical, we didn't find a malicious use for our device, but we're going to make it tamper-proof in case someone did find use for it. Health and safety, we want to make it ergonomic for the user because they're going to be wearing it all day if they want to, and we don't want any strain on the wrist or hand, and we don't want to find out that the vibrations that we're giving off from the armband are bad for the nervous system. Manufacturability and sustainability, we want to make it durable to be used in case it gets bumped or hit, and we want to make it waterproof because it will be worn on the body, and we don't want sweat to interfere with its use.
Some of the engineering standards that we had to look at would be first one particular requirement for concrete vibrators. We can't over vibrate. We also have motor operated electric tools, standards for programmable controllers, wireless networking, positioning devices, communication cables, and standard for manufactured wiring systems. This is our functional block diagram. Arduino will be our microcontroller. You can see our inputs, which would be the on-off switch. The push button would be used for the braille system. The default would be the clock. And if you wanted to view the pedometer, you just hit the push button. It would have a delay of 3 to 5 seconds, and then I'll switch back to the clock. If you want to reset the pedometer, you hold the push button down, and it'll reset the steps on it. And then we also will have a speaker, which will be audio tones for when it turns on, or when you get into a proximity where the ultrasonic sensors will activate. The Arduino Pro Mini has 13 digital input-output pins. We'll probably only have to use a little over half of them. This is the picture of the Arduino Mini. It's actually really compact in size. It's 0.7 inches by 0.13 inches. So it can be you go to hide it into the glove, and then that's the picture of our Parallax ping sensor, which would be we'll position 2 of them in the front of the knuckles of the glove.
This is our parts and price list, everything that we're going to need, or everything that we think we're going to need to build the glove. So we're trying to reuse as much stuff as we can, like for the neoprene and everything, we could reuse the can coolers, or like wetsuit material, the vibration motors we could pull out of controllers or cell phones, anything like that to help keep the cost down. But the most expensive thing is the sensors and the Arduinos, so those we have to have. This is our Gantt chart for all of Capstone 1. It is really one big chart, but it's too big to look at all at once. This is everything that we've had to do for Capstone 1 down to the final report. For end product demo, we want to have everything on the glove tested and working. We want to do a live demonstration, but then also we want to have more than one model so that we can send them around class so everybody can look at it close up while we demonstrate it. So, but during the demonstration, we're going to show you how the sonar reacts whenever the user's coming up to something that they could potentially trip over or run into. We want to show how the braille system works. For the clock, it's going to be 24-hour time, and we're going to use LEDs to simulate instead of the push buttons because those are really expensive. Whenever we push the push button, we want to show that it's going to switch over and give you the pedometer reading. And of course, we're going to count our steps while we do it so that whenever we push the button, we can make sure that it does have the right output. Our conclusions, we do want the glove to do everything we say it's going to. We want the vibrators and the arms to work like they're supposed to, the braille clock and everything to output properly. We know it's going to be a really hard project. We know it's going to be kind of expensive, but we should be able to finish it in time and underneath our budget. And like I said before, we're going to use the LEDs instead of the push solenoids. One of the main problems that we found, the sensors, whenever you're coming up to stairs or something that's like really amorphous, it isn't going to know exactly what to say. Like you're going to get random outputs from it because it's going to detect like one stair and then the next stair and then the next stair. Depending on how you're moving your wrist or moving your hand, it's going to detect the top stair and tell you that you're really far away, and then if you point your hand down a little bit, it'll immediately detect the bottom stair and be like, oh wait, no, you're only 2 feet away. So that's one of the main problems that it's going to have. For future improvement, if we end up finishing ahead of time, we could add GPS to tell the user how to actually get to certain places, so then they could use the GPS to tell them where they're going to go, and then the glove would mostly just be to assist them in getting there. We want to try to make it smaller and improve the battery life, maybe have something that you can plug in or recharge like cell phones do, instead of having a speaker on the armband so that everyone can hear it, or if you're somewhere quiet, or even if you're somewhere too loud you can't hear the speaker, we could possibly replace it with a headphone jack or like a Bluetooth so they can hear it straight in their ear without interference from anything else. Any questions?
The neoprene, was that going to be used for the glove that was on the budget list, or what was it? What was that going to be used for?
Everything's going to be mounted to a neoprene glove. So.
Okay. Well, just wondering because, I mean, this is just a consideration, but I know a lot of people, or not a lot of people, but some people are allergic to neoprene. So, I mean, I'm not sure what, the ratio of a blind person to also being allergic to neoprene is, but, that's always another, I guess, consideration of a possibility of they won't be able to use the glove because they're allergic to it, but that's just one of my things.
Thank you.
It's good that you mentioned the step scenario. So what you can do is you can make that an exception in your program so that, because they will have a certain signature, okay? So you can say if you get something like this, you have multiple readings and stuff like that, this might be a step. So you might have like an exception in your program that says, look up, there are steps in front of you or something like that. So that could be handled in your program.
Oh, and the sensors, they send, the frequency that they send is 40 kilohertz, and they send it for 200 microseconds, and then there's a 200 microsecond break, and then it sends out another pulse. So they would be really close together, and if you were moving your hand like up and down or back and forth, it would get really random senses really close together, so that would work.
You said affordable. What does it mean?
That it's a lot cheaper than all the other options by using recycled material.
And how much would be the price?
To build just one of them, we projected 120, and it was at 380, I think, because we're building 3. And we chopped off like $40 by using recycled neoprene.
And it is a little more expensive than a cane, but it's a lot cheaper than a dog, and we feel like it would be more useful.
Yeah, somewhere I need to define what is the affordable mean.